Welcome back to our lecture on quantum information theory. Today we're going to continue with quantum computing. In particular, what we're going to study today are universal gate sets. So in the last lecture we discussed quantum gates which act on multiple qubits. So starting from the CNOT gate, we found a controlled unitary gate and the decomposition of this into CNOT and single-qubit gates. We then continued to controlled unitary gates on multiple controls. One particular instance is the Toffoli gate. For the Toffoli gate, we also wrote down a decomposition into CNOT and single-qubit gates. And with the Toffoli gate, we then found a nice expression or a nice circuit diagram with which we can implement the controlled unitary gates with multiple controls. Okay, so all of this was for a particular purpose, namely for the purpose that we can prove in the end that there's such a universal set of gates with which we can implement any unitary gate of an n-qubit register. Okay, and today we start with this proof. So it's going to take some time, and the proof is subdivided in 3 parts. So I say it again. What we now want to prove is we want to show that any arbitrary unitary gate operation on n qubits can be approximated with arbitrary precision by only using the CNOT gate, the Hadamard gate, and the T gate. Okay? So this is chapter 2.3. And the proof is subdivided in 3 parts, namely, so first I'm going to write down, so we now show that any unitary on n qubits, on n qubits can be decomposed or can be approximated to arbitrary accuracy by combinations of CNOT, Hadamard, and T gates. So we proceed in 3 steps, showing that first we show that any n-qubit unitary can be decomposed into 2-level unitaries. Second, we show that any 2-level unitary can be decomposed into CNOT and single-qubit unitaries. Into CNOT and single-qubit gates. And the third part is then showing that any single qubit gate can be approximated to arbitrary accuracy by compositions of hard-domain T gates. So any single qubit gate can be approximated to arbitrary accuracy or say by a finite set of Hadamard and T gates. So we start now with the first point, namely we now would like to decompose an arbitrary n qubit unitary into so-called two-level unitaries. So this 2.3.1. Okay, and in order to see how this works, this decomposition, I'd like to go through a basic example. And with this example of a 3x3 unitary, we can then infer the procedure for an arbitrary d by t d unitary. Okay, so let us to see the essential idea. Consider the example of a 3x3 unitary. So let me write this down as A, B, C, D, E, F, G, H, J. It's equation 2.48. So what we want to do now is we want to write this in this way. So we aim, or say we want to find two-level unitaries U1, U2, and U3 such that U3, U2, U1, U is the identity, and hence U is equal to U1 dagger, U2 dagger, U3 dagger. So this is our aim now. Now see, we have U, and now we want to multiply this by this two-level unitaries, such that in the end we get the identity. If we found these unitaries, we definitely know that U1 dagger times U2 dagger times U3 dagger must be U, okay? Because all of this is unitary. So let's first go back to this unitary. So what we do now is we take a two-level unitary such that this element B is eliminated. Okay, such that if we multiply it with U1 from left, there in this entry B we get 0. This is the first step that we do. So first we eliminate B. In equation 248. By multiplying with u1 is equal to, okay, now let me write this down. We have A complex conjugated divided by A modulo square times B modulo square. Then we have B complex conjugated divided by A squared plus B squared square root. Then we have 0. Here we have B divided by A squared plus B squared and minus A divided by A squared plus B squared. Then 0. And then we have 0, 0, 1. Okay, so you can check that this is indeed a unitary matrix. So this is indeed a unitary matrix, and if we multiply this, so if we take u1 times u, then we get some elements which I don't specify further, namely A prime, and then here instead of B we get 0, this is what we wanted, and then some C prime, E prime, E prime, F prime, G prime, H prime, J prime. Okay, so this was the first step. So this, you see, is a two-level unitary, meaning that there are non-vanishing elements in a 2x2 subspace, okay? And otherwise it's the identity in the other subspace. This is what we call a two-level unitary. And if we multiply it, then we can eliminate this B element, okay? And I don't specify further these other elements, okay? They can be non-vanishing in general. And now let's do the same trick and eliminate C prime here, okay? So now we have here 0, now we want C prime also to be 0. And we can do the same trick and multiply with such a two-level unitary in order to get rid of C prime. So we have now similarly by multiplying with u2 is equal to A prime divided by A prime squared plus C prime squared square root. Then we have 0 and, sorry, this is complex conjugation. Then C prime complex conjugated and A prime squared plus C prime squared. And then we have 0, 1, 0. And C prime divided by A prime squared plus C prime squared, 0 and A minus A prime divided by A prime squared plus C prime squared. So if we multiply now u2 from the left on u1 times u, then we eliminate C prime. Okay? So you can do this, I think you can do this without any calculations to see that this is indeed true, because you only have to calculate actually one element of the matrix multiplication. So what we get is, we get u2, u1 times u is equal to a prime prime 0. So this must be a 1. Okay, 1, 0, 0. Then we have d prime prime e, f, g, h, and j. Again, those other elements, I don't further specify them, right? This is equation 252. And now, since u2, u1, and u are unitary, the same must hold for the product. So, since u2, u1, and u are unitary, u2 times u1 times u must also be unitary. And for unitary matrix, we have that here d prime times d prime prime times and g prime prime must be 0 because of orthonormal columns and rows of a unitary. Such that d prime prime is equal to g prime prime equal to 0. So we have u2, u1 times u is equal to 1, 0, 0, 0, 0, and then we have e prime prime, f prime prime, h prime prime, j prime prime. And what we do now is we multiply with another two-level unitary in order that this gets the identity. Okay. Now multiplying by u3 is equal to 1, 0, 0, 0, and then we have e prime prime star. Here we have j prime prime star, and here we have h prime prime star and f prime prime star. So this leads to u3 times u2 times u1 times u is equal to the identity. And this is actually what we wanted. So, because now we know that u must be equal to u1 dagger, u2 dagger, u3 dagger. Right? And this is exactly what we wanted. We now decomposed this 3x3 unitary into a product of two-level unitaries. Okay, and this is the essential idea behind this. If we now go to d by d unitary, we can do the same procedure and start eliminating this first element in the first row, in the second element in the first row, the third element in the first column. Okay. Second element in the first column, the third element in the first column, and so on. And this we do simply by multiplying with such two-level unitaries. And what we then get is a unitary of this form, where we have a subunitary in the upper and the lower right corner left. Okay? And then with this subunitary, we can do the very same procedure, reducing this by one dimension. And with this procedure, we can go through all subunitaries such that in the end we get the identity. And once we got the identity, we know the decomposition into two-level unitaries. Okay. So repeating this procedure. Oh, sorry. So in general, if U is a d by d unitary, we similarly find two-level unitaries U1 to UD minus 1 such that UD minus 1 times U1 times U is equal to 1, 0, zeros. And here we have a subunitary V. So, and then we can repeat this process for the subunitary V. And for all further subunitaries, this leads to essentially then to the decomposition into two-level unitaries. It leads to the decomposition. Okay, now K, so the number of two-level unitaries, is d minus 1 plus d minus 2. So for to get this procedure that we eliminate one column, we need d minus 1 two-level unitaries, as you can see here. Now for this subunitary, to do the same procedure for this one, we need d minus 2 two-level unitaries. Right? And then we go smaller and smaller until we are left with a 2 by 2 subunitary for which we need one two-level unitary to diagonalize this. Okay? So in total, K is smaller or equal to this number here. So, and this we know, this is d times d minus 1 over 2. And now, recall that we considered a general d by d unitary, right? If we now have n qubits, then the dimension d is 2 to the power of n. Okay? So for an n qubit unitary, we have d is 2 to the power of n, such that the number of two-level unitaries we need, k is smaller or equal, let's plug this in, 2 to the power of n times 2 to the power of n minus 1 over 2, which is 2 to the power of n minus 1 times 2 to the n minus 1. So and this grows exponentially in n. So it grows as O 4 to the power of n. So it's 2 to the power of 2n, which is O 4 to the power of n. So for this decomposition, you already see here, for this decomposition, in this, if you do it in this way, we need an exponential number of two-level unitaries. Okay, with this we finished now the first task, namely we showed that any n-qubit unitary can be decomposed into two-level unitaries. Okay, the second task was, and this we're going to show now, is that any two-level unitary can be decomposed into CNOT gates and single-qubit unitaries. So again, I'd like to present the essential idea with an example. And as an example, let's take 3 qubits. Such that the dimension of such a 2 by 2 level unitary is such that d is equal to 2 to the power of 3, which is 8. And consider the following 2 by 2 unitary. And the following two-level unitary, sorry. Okay, all the other entries are 0. I mark this in this way. So it has only non-vanishing entries here. It's A, B, C, D, and then the diagonal, which is 1. So this is such a two-level unitary. I write this down in red such that you can see this. So we have A, B, C, and D. That this two-level unitary only acts non-trivial in this subspace spanned by the first and by the last state, right? And in our usual convention of the matrix representation, these states correspond to 0, 0, 0. So this one is 0, 0, 0, and this one is 1, 1, 1. Okay, this is just an example. So we're aiming at a way such that we can implement such a two-level unitary with quantum gates, right? So far it's simply a matrix in a matrix representation. And yet we don't know how to implement this matrix. And this is what we want to do now. We want to find such an implementation in terms of CNOT gates and single-qubit unitaries. So what we see here is, I write it down, we see that U only acts non-trivial on the subspace spanned by the basis states 0, 0, 0 and 1, 1, 1. Okay, but with the embedded unitary, let's call this V. So, and you see, I now extracted this unitary V, which acts on the subspace spanned by these two basis states. And you see this is essentially, it's a 2x2 unitary, and this is essentially, if you boil it down, you could implement this by a unitary on a single qubit, right? So what we want to do now is, our aim is now to take this subspace, transform this into a subspace such that we can act with a single qubit unitary V and then transform back into this subspace spanned by 0, 0, 0 and 1, 1, 1. Okay? And if we do this transformation, and then we can implement this unitary. So what we want to do now is we can implement U by first mapping 0, 0, 0 to, say, 0, now I write times 1, 1, and 1, 1, 1 to 1 O times 1, 1. Then second, so once we've done this mapping, you see that we can now implement this unitary by a unitary on the first, acting on the first qubit, which is controlled on the second and third qubit, right? Because the second and third qubit must be 1. If we do this transformation from this state to this state, and if we implement, so to say, a unitary on the first qubit, condition on the second qubit, and transform back, then this exactly realizes what we want to have, namely a unitary acting on this subspace 000 and 111. Executing V on the first qubit. Conditioned on the second and third. Qubit. And 3 map the back transformation 0, 1, 1, and 1, 1, 1, back to 0, 0, 0, and 1, 1, 1. So if we proceed in this way, then we can implement this two-level unitary. Let me say it again. We take the subspace in which this unitary is acting non-trivially. This is this subspace here, spanned by these two basis states. And then we map this onto these states such that we have the first state is 0 in the first qubit, and the second is 1 in the first qubit, and they coincide in all the other qubits. And now we can implement V by a unitary acting on the first qubit, which is conditioned on these states of the other qubits. And then we simply have to transform back. So have to invert this transformation to get back to this representation here. And this way we can implement this two-level unitary. And in order to do this, we use a so-called gray code. Okay? A gray code, which is a sequence of n qubit or n qubit registered states which differ by the state of a single qubit only, or which differ by one qubit state only, which differ by one qubit state only, and connect the two states on which U is acting non-trivially. Okay, so again, what is a gray code? A gray code is a sequence of n qubit register states, so a sequence of 0, 0, 0s and 1s of n qubits. And the sequence is made out of n qubit register states which only differ by one qubit and which connect the states where this unitary acts non-trivially on. Okay, for our case, it would be the two states would be 0, 0, 0. So let's call this qubit A, qubit B, and qubit C. So we have 0, 0, 0, which would be then 0 in A, 0 B, 0 C. Okay, and now we want to go to 1, 1, 1. And in each line, we are only allowed now to flip the state of one qubit. So then we have here, say, first we flip the qubit C, then we flip the qubit B, and then the qubit A. Okay? And such a sequence is called a gray code, which connects the states 0, 0, 0 and 1, 1, 1. Okay, by flipping one qubit only. And we can now use this gray code in order to find a circuit which implements this. let me first write down this circuit and then explain how it works. So we give this gray code a number, it's 262. So from the gray code (262) and steps 2 and 3, we find the circuit so we have qubit A, B, and C. Okay, so first, if we have the state 0, 0, 0, we have to flip the third qubit conditioned on the 0 of these first 2 qubits. Okay, so qubit A and B are conditioned on 0, and conditioned on this, we flip this third qubit. Okay. Next, so we are here now at this line. On the next line, we have to flip the qubit B, conditioned on a 0 in A and conditioned on a 1 of C. So we flip qubit B, and A is conditioned on 0, and C is conditioned on 1. Okay, and now what you see is, what we did now is we transformed the state 0, 0, 0 into the state 0, 1, 1. Right? This is exactly what we wanted to do. State 0, 0, 0 is now transformed to 0, 1, 1. And the state 1, 1, 1 is transformed to 1, 1, 1. So it stays the same. If you go through the circuit, it stays the same. So if we have 1, 1 here, then there is no flip because these are conditional 0. Right? And if you have 1 here and 1 here, again, there is nothing happening because this is conditioned on 1. Okay? So what this does is it transforms here our state 0, 0, 0 and 1, 1, 1. It's first transformed to 0, 0, 1, and this remains the same, and then it's transformed to 0, 1, 1, and this remains the same. Okay? And what we can do now is we can do the second step. Now we execute this unitary V on the first qubit conditioned on the second and the third qubit. Okay, so here now do a unitary V controlled on the state 1. So I control on 1 and of the second and third qubit. Okay, and now we can go to the third step. The third step says, okay, we have to transform back. And this is very simply done by recognizing that these controlled NOT gates are self-inverse. Okay, so we simply do the same sequence, but now from right to left. So, which gives us this. Well, this is all what we wanted. So we now, with this circuit, we now implemented this this two-level unitary U, which has as a sub-unitary this matrix B. First, the sequence transforms the basis states on which our two-level unitary acts non-trivially onto these basis states 011 and 111, such that we can implement a unitary on the first qubit, conditioned on the state of the other qubit. This is what we do here, and then we simply transform back. So here the first two controlled NOT gates transform then the controlled unitary is applied conditioned on the state of the first and second qubit. And the last two controlled NOT gates transform back via 0, 1, 1 goes to 0, 0, 0, and 1, 1, 1 goes to 1, 1, 1. So now let me write down the conclusion, or let me state the conclusion. The conclusion is that we found now a way how to decompose any d by d unitary into CNOT gates and single qubit gates. The reason is that we decomposed this first into two-level unitaries. So we decomposed, so to say, an arbitrary d by d unitary into a product of two-level unitaries. And now we've seen that we can implement two-level unitaries by such controlled gates. And in our last lecture, we have seen that these controlled gates can be decomposed into CNOT gates and single-qubit unitary gates. Right? So with all these decompositions that we seen at the last lecture, we now know how to decompose an arbitrary n-qubit unitary into CNOT gates and single-qubit gates. Okay, I think this is a good time to make a break and suggest to meet in 10 minutes. Okay, before we continue to the third part of our proof, I'd like to conclude this part. As I mentioned before, together with these decompositions that we've seen last time, we now actually proved that any n-qubit unitary can be decomposed into CNOT gates and single-qubit unitaries. So, in conclusion, together with 2.31. This I think was the decomposition of a single qubit of a controlled unitary with a single control. Then we had 2.36. This I think was the decomposition of the Toffoli gate, and 2.37, and this was the decomposition of a controlled unitary with multiple controls in terms of Toffoli gates and a controlled unitary with a single control. So together with this equation, we now showed that single qubit gates and single qubit CNOT gates. They are universal, meaning that you can build every n-qubit gate from these gates. So since the concatenation allows to implement arbitrary d by d unitaries. But we can now ask how many of these unitaries do we actually need? So how many gates are needed? First, if we remember this circuit that we got from the gray code, there you see that we need 2 times n-1 controlled NOT gates and 1 controlled unitary gates. So a 2-level unitary call this UJ dagger, requires at most 2 times n-1 controlled NOT gates. And 1 controlled unitary. And each of them require ON CNOTs and single qubit gates. So each of them require ON CNOTs and single qubit unitaries. Hence, UJ, so our 2-level unitary requires ON squared gates. Okay, so we need a number linear in n for each 2-level unitary, and each of these, so 2 to the n controlled, we need a number linear in n of controlled NOT gates and controlled unitary gates. Each of them requires O to the n CNOTs and single qubit gates, meaning together we have O to the n squared gates. Okay, and this is not shown here. Okay, and this one here is not shown here. I mark it here. Not shown here. But you can find this in the literature. Okay, and I don't want to prove this here. And then, as a next step, in equation 259, which was today before the break, we found that O4 to the n 2-level unitaries are needed for an n-qubit unitary. So in total, arbitrary unitary operation in n qubits can be implemented using this decomposition method. Can be implemented using the circuit containing O n squared 4 to the power of n single qubit and CNOT gates. So since this number is exponentially in n, it's in general difficult to find fast quantum algorithms with this method. Okay, so while we did find a decomposition now into single qubit and CNOT gates, the drawback is that we need a large number in general, right? So this is an estimate. And indeed, this is it's not so easy to find an efficient implementation of unitary gates. And fortunately, for some unitaries, we know efficient ways how to implement them. One example is the Fourier transformation, which we're going to discuss in a while, I think next week. And this Fourier transformation is the key for many quantum algorithms. And for this, it's fortunate that we do know an algorithm or a circuit diagram which can be implemented efficiently. Okay, now I'd like to start with the third part. Okay, namely, I'd like to show now that every single qubit unitary gate can be decomposed into Hadamard and T gates. Okay, what's the motivation? The motivation is that usually if you do computation, you'd like to do a universal computation with a finite set of gates. Okay? Now think of classical computation. So what's in our computer is a realization of a finite set of classical gates. Okay? For example, one can show that the NAND gate is universal. So in the end, if you want to build a classical computer, it's enough for the industry to build good NAND gates and to build a lot of them together, right? And similarly, we now would like to find out whether we can do universal quantum computation also with a finite number of gates. Okay? So far, we found a decomposition to CNOT gate and single qubit unitary gates, but there is an infinite number of single qubit unitaries. Remember that these single qubit unitaries correspond to a rotation on the Bloch sphere, right? And I can find infinitely many rotations there. So the question is now, can we approximate any such rotation by a finite set of single-qubit unitaries? And it turns out that there is a finite set, and as we will see, as we will show now, is that the Hadamard and the T-gate together form such a set, meaning that altogether the CNOT, the Hadamard, and the T-gate form a set for a universal gate set with which we can implement any n-qubit unitary. Okay? So this is now chapter 2.3.3. Approximation of arbitrary single-qubit gates by Hadamard and T-gates. So before we can prove this, we need some more tools. Namely, we need a tool how we can compare whether an approximation is good or not. Okay, so we need a method which tells us how good is this approximation to quantify how well we can approximate a unitary. And with this is, so to say, goes hand in hand with the approximation of the error that we do. Okay, and with this can be resolved by the following definition, which defines the approximation error. So it's definition 2.3. For V, a unitary which approximates the unitary U, approximation error is defined as, okay, we denote this by E of U and V. So it's the error, which is a maximization over all normalized states, and we maximize over the norm of U minus V acting on the state psi. Where the maximization is over all normalized states psi in the Hilbert space H. Okay, so as I told you, we first need these tools, and next we need some properties. So two properties of this approximation error. And once we know these two properties, we can continue and prove that any single-qubit unitary can be approximated to arbitrary accuracy by Hadamard and T-gates. Okay, so let's now continue with these properties of this approximation error. So first, this approximation error gives an upper bound between the output statistics if I perform an arbitrary measurement of U psi and V psi. Okay, so E of UV gives an upper bound for the difference between the measurement statistics derived from measurements of u psi and v psi for arbitrary psi and arbitrary measurement operators. Okay, let's recall this. Suppose you have this state u psi. So since u is unitary, this is simply a normalized state. And the state v psi, again, this is simply a normalized state since v is unitary. And now we perform any measurement on the state. So suppose we perform a measurement and then we compare the outcome. Okay? And by comparing the outcome, I mean that we calculate the difference of the probabilities. And what this here states is that the difference of these outcomes is bounded from above by this approximation error. So it tells us, this approximation error tells us, okay, if the better we can approximate it, the smaller must be the difference in the output statistics, which is actually intuitively clear if we connect this definition here of the approximation error with indeed an error of the approximation. Okay, so it has a meaning in terms of measurement statistics. And I'd like to prove this now. Okay. Before I prove it, I'm going to erase this board. Okay, so let's prove the statement. So for measurements, on the state u psi and v psi, so the outcome or the output probability is P, so for U is equal to trace of M dagger M, and then we have U psi U dagger, which is equal to psi u dagger m dagger m u psi. And for v similar, it's the trace of m dagger m v psi v dagger, which is psi v dagger m v psi. And now we can calculate the difference. So let's calculate the modulus of Pu minus Pv. Okay, we can plug this in here, which is psi u dagger m u psi minus psi v dagger m v psi. Okay, now we're gonna rewrite this a bit. So what we did is we introduced a term here, namely this term here with u dagger on the left and v on the right. This is what we introduced here, and here we actually we took, and here we subtracted again. So it's so I think this must be vice versa. Correct, minus minus plus. It's okay. U dagger y minus plus u dagger v dagger. It's okay. Was okay. And here we subtracted it again. Okay. So let's go from this line to this line. Here we introduced an additional term, minus y, which is then, so we have on the left u dagger, on the right y, and this we have here with plus, so we have minus and minus gives plus u dagger y, and then the same as above. So we simply have minus 1 plus 1 here, okay, and this we can now approximate. So this must be smaller or equal than this expression here. Okay, so we simply split the modulus into these two parts. With the modulus of a plus b must be smaller or equal to the modulus of a plus the modulus of b. Okay, and next what we're going to use is so we use the following, namely first we use Cauchy-Schwarz inequality. Which is x, y, smaller or equal to the norm of x times the norm of y. And we further use that the norm of m dagger m u minus y psi must be smaller or equal to the norm of u minus y psi. Okay, remember those m's. If you have m dagger m, it's a positive operator. Okay. And okay, now using this in this equation, which is 265, this yields that Pu minus Pv is smaller or equal to the norm of psi u dagger and times the norm of this is smaller equal to u minus v psi plus the norm of psi v dagger minus u dagger times the norm of v psi. Okay, this norm here is 1. So we have equal to u minus v psi plus u minus v psi. So we rewrote this part, which is 2 times norm of u minus v psi. Okay, now we can take a look at the definition. Okay, and there is no maximization, meaning that this is smaller or equal to 2 times e of uv. Okay, and this proves now that this approximation error is an upper bound of this difference of the output probabilities for an arbitrary psi and an arbitrary measurement m. Now there's one more property of this approximation error that we need. So remember that we decomposed an arbitrary n-qubit unitary into products of 2-level unitaries. And we now would like to see how this approximation error behaves if we have products of unitaries. Namely, so this is remark 2 for unitaries uj and vj. The approximation error satisfies that E of U1 times U2 to UM and V1, V2 to Vm is smaller or equal to the sum of the approximation errors of the individual unitaries. So let's prove this. The proof is fairly simple. We prove by induction. Starting with m is equal to 2. So we have E of U1, U2 and V1, V2. Okay, let's plug this in the definition. The definition says this is equal to the maximization over the states psi in H, and we maximize over the norm of now U1, U2 minus V1, V2 psi. Now let's rewrite this. So let's write this as U1, U2 minus U1, V2, or let's make it different, minus V1, U2 psi plus U1, U2, so that we have plus V1, U2 minus V1, V2 psi. So again, we added something that we also subtracted. So it's this one, this part, V1, U2, here with the minus, and here V1, U2 with the plus sign. Okay, now we use similar as before, that this norm must be smaller or equal than the norm of the first part plus the norm of the second part. So we have E of U1, U2, U1, U2 smaller equal to the maximization over sin H, and then we have the norm of, okay, the first part here we can just write this as U1 minus V1 times U2 psi plus the second part, we can write this V1 times U2 minus V2 psi. Okay, now what we recognize here is that this maximization goes over a state psi, which now appears here and here, right? So we don't have a maximization of this and a maximization of this. And the next thing, we recognize that this U2 times psi is also simply a state, a normalized state in our Hilbert space. Okay? And here we recognize that this norm, that since V1 is unitary, this is the same as if V1 would not be there. Right? Because V1 is simply a unitary transformation of our state which doesn't change the norm. So we find that this is smaller or equal to E of U1, V1 plus E of U2, V2. Okay, and the smaller or equal to or less equal is because this maximization is not running over both terms. Right? If the maximization, if here would be a maximization only over this term and an additional maximization over only this term, then this would be an equality. But the inequality is because there's only one maximization over both terms. Okay, and with this, we now found our statement for m is equal to 2. Well, and if m is larger than 2, then it follows by induction, right? So for m larger 2, equation 267 follows from induction. Okay, this finishes this proof. And I think I'm gonna stop here today. This is a good point to stop because next time we then we now have everything together that we can prove on Thursday that any single qubit unitary can be approximated to arbitrary precision with Hadamard and T gates. So see you next time.